Okay, so let's start off with this review question. I want to test your remembrance of the terms distance and displacement. I also want to do a quick review of the terms vectors and scalars. And I also want to focus on the terms accuracy and precision. This question is very purposeful because I can talk about a lot of the things we did yesterday all at once. So let me give you a couple seconds to try it if you haven't looked at it already, and then let's work through it as a group. I think I've settled. I'm going to sit here. This is what I'm going to teach from. Which is really just what I did last year in the algebra, isn't it? Yeah, so this feels the best. So. Okay, so even if you're still working, let's do some verbal review of some of the words I just used. Let's start with the words accuracy and precision. I'm a big stickler for those. I mean, they were even on your Chem 30 final last year. I really want you to use those words properly. So accuracy is really a matter of correctness. Some people actually, when it comes to accuracy, they like to think of a dartboard. If you're accurate, you hit the middle of the dartboard, right? If you're aiming for the bullseye, you hit the bullseye. Right? Does that make sense? Right. So if I were to ask you to use an instrument of measuring things, whatever it happens to be, a scale, a stopwatch. Some of you were in my science class last year. We did a thing where Doug Gregory dropped some fruit from the top of his cherry picker, right? And I asked you to time it on your stopwatch, right? How accurate were you pressing start and stop at the exact right moments? I'd say, well, I mean, that's where your accuracy was a problem, right? Where did you actually press start and stop when you were supposed to? Maybe not so much, right? If we were using the scales in chemistry class and the scale was fluctuating, it was bouncing all over the place, and you couldn't get it to settle on a certain number, or maybe like the piece of magnesium was catching on the lid or something like that. Maybe you had that happen before. Then the scale's not operating properly. That's not accurate. When it comes to physics, if we're given a number on paper, though, let's assume that it's accurate. Okay, I mean, let's assume that if it says 16.7, that number is actually correct. There wasn't a mistake made there. When we do a lab, however, we need to always judge the accuracy of the numbers we have because, yeah, maybe we screwed up a little bit in terms of our operation of measuring tools. Precision, though, is a measure of like how fine of a number we have. You guys know what I mean by the number when I say the word fine? Like how little incremental measurements we can have, right? And the smaller of those we have, often that's a good thing too. Which one of these numbers is more precise? The 390283 number, right? If I asked you how precise, I think I'd accept two answers. Like you could say to the nearest 4 decimal places, or if you wanted to walk it out, it would be what, 10th, 100,000, to the nearest 10,000th of a meter, right? In a way, if you remember how to do your units properly, if this is where the meters number is right here, put a pen on. If you were to pull this back 1, 2, 3 decimal places, that would be a millimeter. Does that make sense? Because a millimeter is times 10 to the minus 3. So then this would be to the nearest 10th of a millimeter. Think of how small a millimeter is, right? We're now able to accurately measure that to a 10th of a millimeter. That's incredibly fine. Does that make sense? So those are the two words I want to use there. When it comes to our operations, then adding, subtracting, multiplying, and dividing, we use the term called sig digs. Okay. It's slightly different depending on whether we add or multiply. Okay, second question. Are these scalars or vectors? Why? Yeah, they've included direction, which means that we care which way we're going. So, and that's the main difference between displacement and distance. So why don't I actually start with distance here? Distance is directionless, so I just want to know how far you went total. So ideally, you should have done something like this. You went 16.7. I'm going to dig you on this. If you don't write the word meters afterwards, I want you to get into that habit. Really enforce good habits. and then 39.0283 also meters. And we're just adding them together. So, grab a calculator for the purpose today. Alright, so if I type that in my calculator, I get 55.7283 also in meters. But that's not the right answer, right? Because we need to work with our precision accuracy sig integrals, right? So based on this was only capable of measuring to the nearest tenth. So we kind of need to cut this thing off right here. Should I round up or down? Down, yeah. This 2 right here is not enough that we know that it's over the halfway mark. It might have actually been. This number right here, like this 7 right here, is as far as we measured. It could have been, say, a 1 afterwards. Could have been a 2 afterwards. Could have even been a 3 or a 4 afterwards. This next number couldn't have been a 5 though. Because if this number was a 5, our scale would have registered that as an 8. That makes sense? But let's just do a hypothetical. Let's say this next digit here had been a 4 if we could have measured it. It would have mean 4 and 2 would give us 6, which means we were over the halfway mark. You see how all of a sudden the precision has now affected my accuracy? Because if I told you the answer was 55.7, it actually might have been 55.8, and we didn't have the ability to know that based on our precision. So this is the best we can do though. The answer would be 55.7 meters. That's how far we walked as a distance. And we'd represent that with just a regular old D, no little hat thing on top of it. So far so good? Alright. Similar things then for displacement, only now we care about direction. I'm going to start off by figuring out which way they ultimately went. It looks like they went more west than east, so for your displacement with the little hat, I'm going to put a west in square brackets afterwards, and then I'll just subtract these guys. So 39.0982 minus 16.7, I got 22.3. Anybody else get that? I got 22.3 meters. Start training your brain for that, okay? It's really important. If we were doing math, we're just working with numbers, right? But physics is applied math. We're trying to now assign some sort of quantitative measure to it, not qualitative. You guys get that without my help? Cool. Does everybody have a formula sheet? Because that's where we're going today. We're going to start plowing through a lot of the formulas on there. I think last year we counted, there's like 80 on your formula sheet that we're going to learn over the course of the whole year. If you guys over there by chance haven't printed one off yet, and you don't remember where to find them, go to Physics 20 on my website. Just straight up click on the Physics 20, and there's a whole bunch of the links here. You're looking for a physics data book. So it would look like this. I skipped the first page and the last page, but we're going to focus, sorry, it's sideways here. We're going to focus on a few of these equations right here. Okay. So the next ones we're going to talk about then are speed and velocity. And again, terminology is really important because one involves a direction and the other one doesn't. So if I were to ask you what your speed was driving on the highway, you'd say 110 kilometers an hour. If I were to ask you what your velocity was on the highway, you'd say 110 kilometers an hour west. Right? That's the only difference. In a way, speed comes from distance, and velocity comes from displacement. That's all. So one's a vector, one's a scalar. That's all we need. Essentially, these things describe your rate of motion. Basically, in a way, it's like how fast you're going. So that leads us to, I just said this, you guys can read this. Speed, velocity. Here's the formula. And maybe some of you guys even recognize this from last year. How do you find a speed or a velocity? You take your distance or displacement, you divide by how long it takes you. If I want to know how fast I'm traveling and I don't have a speedometer on my car, I say, well, I traveled 50 kilometers in half an hour. That gives me my speed. The most typical unit of measurement we probably use in everyday life is kilometers per hour. Like, that's just something that most of us, I think, intuitively know once you learn how to drive, right? In physics, though, the main unit of measurement we're going to use, distance is going to be measured in meters, time is going to be measured in seconds. So we normally write this thing in meters per second. If we care about directions, write the little arrow hats on top of it and include some sort of direction afterwards. If we don't care about direction, then don't worry about it. Here's a word that maybe we haven't used before. It's called uniform motion. If I set the car to cruise control and I'm always going the exact same speed, that's uniform motion. You know how sometimes though you might speed up, slow down, speed up, slow down? That's not uniform, right? So, but if you're going in a straight line, if you're going in a constant rate of motion, it's uniform motion. So, is this uniform motion if I'm on cruise control on a straight highway at 100 kilometers an hour? Yeah. What if I took my foot off what if I turned the cruise control off because I wanted to speed up to pass the center? Well, now I'm not going the same speed, right? What if it's on a straight highway? What if I start making a turn? Is that uniform motion? Why? You're not going the same direction, right? So, alright. So let's just do a really basic example. About as easy as it gets. Person's going to walk 10 meters away from a stop sign in 5 seconds. Find me their speed. I didn't give you a direction. It's okay. We're working with speed. That's all. So, here's what I'd like to see from you guys when you start at this. I would say, well, your speed, velocity, is equal to your distance over time. I just realized I might have skipped over something important. Did I? I didn't talk about this. Okay, can we go back a slide here? Do you guys know what the little triangle means? Any of you guys remember what it means? Yeah, it's said delta. It's a Greek symbol, delta. Delta. What does it mean? Good job, guys. That's not a good science teacher. Okay, it's a Greek symbol for delta, and it means change. Essentially means find how much change you have in your distance, because maybe you don't actually have any change in distance, right? What if you stood still? And the last one here is what about your change in time? Often we put these symbols here because sometimes we have to consider like a certain time frame. Like maybe we're going to measure from 3 seconds until 5 seconds. We're going to measure from that point. So if we counted that time frame from 3 to 5 seconds, it's actually just 2 seconds worth that we're considering. Okay, you looking for someone or just?
I'm wondering where your tall table is.
I don't have one.
Did you get one and get rid of it?
Nope.
You never did get one?
Never received one. I get a tall table?
You know what that means?
Lab has one in his room.
Yeah.
Yeah. I never got one.
Would you like one like that was shorter?
Sure.
But cut off?
Sure. Whatever.
Okay.
If you got one. I'll just take more furniture. Alright. Anyways, yeah, if you see these little triangle symbols, it just means find the change in something. You guys who are in chemistry, we had this in one formula at some point. Q equals mc delta T. You guys recall that? Yeah. Right? The delta refers to the change in temperature, right? So if we started at 19 degrees Celsius and went up to 24 degrees Celsius, then this is, we're gonna throw in 5, right? Because it went up by 5. Sorry, I kind of glossed over that. Some of you haven't seen that before. Anyways, to find our speed then, find out how much distance change there is, find out how much time change there is. So I'd say, well, you went 10.0 meters in 5.00 seconds. 10 divided by 5 on your calculator will give you 2. And that's wrong, because we gotta watch our sig. So this time, because we're multiplying and dividing, the difference is we just need to look at how many sig digs we have, right? Someone took the time to actually write these zeros and those zeros out, meaning that it happened to actually land exactly on that marker, right? If Michael Phelps was doing a swimming race, he could actually finish in 39.00 seconds. Could be 39.01 or 39.02, but if someone took the time to write these numbers out, they count as a sig dig. So we got 3 sig digs, so 2.00 meters per second. Does that make sense? We've done this before. Okay. Okay, well, what if I work backwards? What if I give you a speed? What if I give you a time? Can we manipulate a formula algebraically? I mentioned on one of our first days, we have to have some pretty strong algebra skills here. So, I mean, here's what I might suggest in a scenario like this. We're now looking for displacement. So, I mean, we're still using the same sort of formula, velocity, change in displacement, change in time. But the difference now is rather than solving for our velocity, we're actually given that velocity. Technically, it gave us a speed. You see how it was really tricky here, though? It gave us a speed at 15 meters per second. So this is 15 meters per second. But it actually later says that we're going east. So we actually have the velocity. What we don't have is how much displacement we have. But we know that we went 16.8 seconds. You guys still good over there? I hear some chatter.
Oh, we're trying to move the bridging line so we can see the question.
Oh. Yeah, I like this thing up here. Interesting. Oh, it's one on your end that's in the way. I wonder if I can scroll. I really can't scroll up anymore. Is that enough? Sorry, guys. You guys still good with me here? Alright. So, math, how do I get displacement by itself? Times up to 16.8, right? One of the things I really want you to focus on, though, is work on your units. If you really develop your unit canceling skills on the easier units, I think it helps when we get to Physics 30. So if you actually take the time to write this out and go 15 meters per second east times by the 16.8 seconds is equal to your displacement. Check out what happens with your units. So you have seconds in the bottom of the fraction here, and then this seconds is kind of on the top of the fraction. Seconds will cancel. Then you'll do your calculation, so 15 times 16.8. I get 252. I'll fix the sig gigs in a second. What's left for units? Well, the units that I haven't canceled is this meters right here, so it must be meters. And I haven't actually canceled a direction either. Sometimes directions can actually cancel as well, so I'm left with meters east. That's how far my change in displacement was. Why is that wrong? I only get 2 sig gigs. So I have to find some way to fix this issue, right? Because the 15 meters per second limits me. The whatever we measured it on only gave us 2 digits of precision, so we need to fix this. So I'd say there's 2 most common ways of doing it. One would be to call it 2.5 times 10 to the 2 meters east, and slide that decimal place over twice. That works. The other way of doing it, change the unit type. What is a 10 to the 2 on your data sheet? Does it actually give you one of those? A 10 to the 2? Hecta or something like that? Hecto? What's the letter for it? I haven't hardly used that one. It's just straight up H? Okay, so another option is you can call it 2.5 HM east. That's kind of awkward. No one ever uses hectometers, really. I guess another option, we can make it 0.25 kilometers east. That'll work. Maybe I'll move the decimal place over one more time. It doesn't make it a 2.5, it makes it a 0.25. But then rather than having to work in hectometers, you can work in kilometers. If it's written response, I really don't care. But make sure you catch that sig dig issue, because it makes a difference. Like I've been harping on even for some of you kids in math 20. Rounding is an issue, right? We always are going to need to round at some point. And so we need to know how accurate we can be confident in without losing that accuracy, right? Because, I mean, you can imagine in physics, if you're building a bridge, a spaceship, right? Little imperfections over time cause problems, right? Any questions on that? Okay. Here I got 3 examples. Why don't I give you guys, say, a couple minutes to work on those? Once you've done that, maybe take a quick break. We don't have enough time in class for me to give you like 5-minute breaks right once you're done in the hallway. But I mean, the water fountain and bathrooms are just here. So try these 3 if you haven't kind of already. Take a quick break, and then why don't we say at 20 after, let's go over. Does that work? So if you have issues, you're struggling with it, call me over. I'll give you a hand. So 20 after. Yeah.
Where's the displacement set?
You're just gonna have to put in square brackets home plate. That's the direction it's going towards. Does that make sense? Like sometimes you can't go north, south, east, west, up, down. So you just have to put in square brackets like towards home plate because that's the way he's throwing it. Does that make sense? If we had some sort of compass or something like that, we could actually, know the north, south, east, west amounts. So just make sure you catch that that's the way he's throwing it. He's not throwing it towards third base or second. You know what I mean? So, yeah. Put whatever you need to indicate direction in the square brackets. Good question. They have bells over there. They don't have bells yet. That's not right. Here's the first two on the board, because I'm guessing most of you guys have gotten about that far. Any issues with getting 1.83 on the first one? Well, it's pretty straightforward, just about the two dice. Second one, you need to do a little algebra and take that time, times it by 34 meters per second. Sig digs are an issue though. You get 129.2, so you need to find some way to fix that sig dig issue. I feel like the most logical way of doing that is make it 1.3 times 10 to the 2. And just make sure you include the fact that it's, like Jimmy asked, which direction it's going towards home plate, I guess. Any issues on the first two? Okay. What's the issue with trying to do this last one using 2.5 kilometers? Yeah, I haven't done an example like this yet, but if you try to use kilometers and meters per second, the units won't cancel when you actually try to do it properly. So you want to make sure your units are compatible. So for this last one, you're going to want to do something like 340.29 meters per second and make that 0.00 meters. What were you changing time? You want to make sure that your units are compatible, because when you eventually try to cancel this meter sign right here, with that sign right there, if one of them's a kilometers and one's a meters, that's not gonna jive. How do you rearrange this? Good, yeah. Yeah, so time goes up here, the 2500 divides by that number, so your time should be 2500 divided by 340.29. I got 7.3. Sound good? Cool. Take a quick break, like 2 minutes, just to kind of stretch, use the bathroom, grab a drink if you need, and then we'll talk about acceleration in a second. So, take a quick stretch break. Remember that?
No, but I have to learn somewhat.
Does that make sense?
Yeah. Just the one where you have to like do it backwards.
You have to like rearrange them?
Yeah.
Oh, yeah.
Like I was getting it and then the thing.
Okay. I was basically right as you were finishing.
Mm-hmm.
Okay.
I'll be in like a box.
Okay. Yeah, I got lots of questions for us to work on, so. There are like 180 questions now on practice. What do you guys, any issues? Okay. Make sure you'll know. Okay. So what I'll show you. Let's just put it up. What do you guys? Still work. Alright. I mean, really, it's just applied algebra, right? Like, you use the formula, make sure you know where things go, rearrange them. Just don't miss the details, right? Like units and stuff. Okay. Okay. Sounds good. How are things going for you guys over there? Any issues, questions? Thumbs up, I see. Okay. I had asked earlier, but I never actually got a chance to really fully get your response. I sent out emails to what I was thinking were your Gmail accounts. Has anyone checked yet? Okay. If you guys get a moment, can you check and let me know whether somehow I got an email to you? I feel like that's the best way to correspond, because sometimes over the computer thing is challenging. So it gives me a chance to type. I mean, it's not easy sometimes to type answers to physics questions, but at least we can, you get what I'm saying here? So, sorry, what was that? Oh, I need to back off then? Sorry. Okay. Okay. Anyways, if you get a chance, check that email. Shoot me back one just so I know you received it. That way we have a way to try to communicate more than just over this. So, awesome. Okay. Let's move on to acceleration then. Here's what maybe seems crazy, because if you were in my grade 10 class, what we've accomplished so far would have taken us like, I don't know, a week and a half, right, just to get to that point. And after we've done it now, it's like, oh, we can just fly through this, right? So, because at this point, all we're going to now do is just add more formulas. Really, they function the same way. Throw in your units, rearrange for whatever value you're looking for. So we should know some of the little details about them. So the next one is acceleration. Acceleration is basically how fast you speed up or how slow you hit the brakes kind of thing, right? Like this is where you change your speed. If you have acceleration, you do not have uniform motion. Let me say that one more time. If you have an acceleration, you don't have uniform motion. Because a uniform motion means you have a constant velocity. So here we're talking about either you're passing the truck on the highway, right? So you're hitting the gas, or you need to slam on the brakes all of a sudden. Those are the two main ways of doing it. So positive acceleration then is speeding up. Negative acceleration or deceleration is slowing down. So for right now, we're just going to focus on the first one. If you want to accelerate an object, normally you just change the speed. But that's actually not technically true. We'll do this more in the circular motion unit. When things start going around a curve, like if you talk about a banked curve, like going around a radius of a circle, but you can actually accelerate an object by changing its direction. For example, anybody ever gone on like a ride, like say the teacups, where you go spinning around in circles, and you can kind of feel the G-force a little bit? Kinsey Ann and I went on the new water slides at Henderson. Anybody actually see the new water slide park in Lethbridge at Henderson? It's actually really fun. Kinsey's old enough that she can go on it by herself. It was awesome. And there's one section there where the curve is tight enough that you can kind of feel it a little bit, if you know what I'm talking about, where it's like you can feel that acceleration the same way that if like you were in a car and someone just all of a sudden hit on the brakes or sped up, your body can sense that force a little bit, right? And so you can actually accelerate just due to changing your direction. Okay. But for right now, we're just going to focus on your speed changes. So here's your formula. To find a acceleration, find out how much change in speed or velocity you have, find out how much change in time you have. That's all. The units for this then are either written as meters per second per second. I'm actually going to spell that out. Sometimes we'll call it a meters. Oh, we just lost them. Meters per second per second. That's how you'd say that one right there. Or this one right here, you would say meters per second squared. Essentially the way it works from like a math point of view is that you've got a meters on the bottom on the top of a fraction. You've got a seconds on the bottom of a fraction. And there is a seconds on the bottom of a fraction. I'm going to see if I can fix this here. Oh, they're back. You guys back? That was weird. Okay, you didn't miss much. I was just talking. You can probably see it on the screen, just verbally how to say meters per second, or meters per second squared. That was weird. Okay, let's, actually before I do that, I've got an animated GIF here that can kind of illustrate the concept here. So you got three cars here, right? Which one had the highest initial acceleration? Yeah, you can see red, right? Look how fast red gets at the top speed, right? But who wins the race? Yeah, who's that at the bottom? Blue, I guess? 100-meter dash. The best guy in the world is Usain Bolt, right? Usain Bolt is actually very poor at accelerating, right? If you watch the commentators talk about him, if you know what I'm referring to here, he's actually very slow out of the gates. It takes him a little while to get to top speed, but he has a high top speed, right? So this guy down here, this is Usain Bolt. He will have a high velocity by the time he's done. He's going quite fast, right? But this guy right here, the red one, has the highest initial acceleration. But he's now at top speed, and so his top speed is way worse than the blue one right here. Does that make sense? So they are different between the two. Okay, let's do an example. So a boat can accelerate at 4.5 meters per second squared. If it undergoes a change in speed of 18.5 meters per second, how long is it going to take? So again, this is really straightforward. Find a formula, plug some numbers in. So your acceleration is equal to your change in speed. I guess I should take the little arrow hat off since we're not doing directions right now, are we? Just to be consistent. Over a change in time. We know our acceleration is 4.5 meters per second squared. We know our change in speed is 18.5. And we'll change in time. Quick side note here, just to refer to this change in thing here. The reason why we use the little delta symbol for change in is that we don't know that the velocity is going to start at 0 and end at 18.5. It could have started at 15.5 and gone to whatever 18.5 more than that is. So all we know is how much change there is, but it doesn't mean that it's starting from a stop or that it's going to stop. Does that make sense what I'm saying there? So all we know is how much difference there's going to be in the velocity. So Okay, this is just the same as the one I asked Michael about a little while ago. Change your time and your acceleration around. So change in time is equal to your 18.5 meters per second. And I'm going to write out the units the other way this time. I'm going to write out 14.5 meters per second, just so that you can visually see how they cancel. Because this meter will cancel that meter. This second will cancel that second. What's my only unit left? Seconds, right? Mathematically, though, you see how this is the top of a fraction? And this is like the bottom of the bottom of a fraction? You know how like two negatives become a positive kind of thing? If you're on the bottom of a fraction, you're actually back to being on the top. If that makes sense? I can go through the math steps later, but anyways, long story short, seconds. So 18.5 divided by 4.5 gives us 4.1 repeating. So make it 4.1. Straightforward. Okay. Well, that took us probably a couple of days back in Science Dev. Believe it or not, right? Like it's slow going. But I mean, I feel like I'm okay if we just go with the one example. Because now we get to this point now where we can work with all of these different variables, distance, speed, acceleration, time. And at some point here, we then started to add more formulas to the list. Right? And so here are a couple other formulas. Yes?
What does the AB mean on the...
Oh, AB, average.
Okay.
Yeah. So which one is that one? Is that distance over time?
Yeah.
Yeah. So that just means it's an average velocity, right? For that one, we'd be talking about uniform motion. That makes sense? So like how fast is your, like find your total distance, find your total time, find out what your average speed is. Okay, so here's some more formulas. And if you were in my grade 10 class, you might recognize these ones. Essentially, the only difference is that they now include an extra little subscript. See how down here there's either an I or an F? Remember? Initial and final. Yeah, that's all. So these are formulas that have been developed that let us know this is what your starting speed was, this is what your ending speed was. That's all. So rather than working with changes in velocity, now it's referring to where did you start, where did you finish. So depending on the information you have, you just pick one of these formulas. And they're both on this sheet, correct? They should be. Okay. They're both on there?
Yeah, they are.
They're both, okay. Okay. So really, the only challenge here, I would say, is have to make sure you're careful with, like, say, the squared symbol over here. Like, there's just more variables. For you guys who have done grade 11 math all the way through, this is a quadratic equation. I guess we talked about quadratics the other day. Why is it quadratic? The highest power is 2, yeah. So there's actually a lot of strong overlap between grade 11 math and this section of physics here. In a way, this is kind of your constant term. This is a term that has a t, like think of t as x. And then here you've got an x squared. So there's actually a lot of similarities here. Let's try an example. You'll recognize these questions because you're going to have more information now. Rather than giving you, say, 2 pieces of information, these ones probably give you 3, right? You've got a meters per second, you've got 20 seconds, and you've got a speed. So here's one of the things that I try to encourage kids to do that after a while. Unless you're really good at knowing which formula to use right off the bat, I like to just quickly write down the information you have. Because sometimes you get a lot of information in questions, especially the further in we get. So I might say, look, we have a deceleration. So that's my acceleration of 4.5 meters per second. I'm just going to write that one down in the corner, but I'm actually going to add something to it. Yeah, throw a negative sign in there. Why? It's decelerating, it's slowing down, yeah. I need to make sure I'm careful on the negative side. I also have a time. My time is 20 seconds. I have a speed of 2.0 meters per second. Is that my initial or final speed? It kind of implies that we need to slow down to a speed of 2 meters per second, so it looks like it's a final velocity. And we're looking for a distance. So sometimes I like to recommend just quickly write out the information you have. you can probably imagine when we get to a higher level, sometimes you get lots of information, including extra stuff that's not even relevant. Right? So just write down the stuff you have. And now let's go to our formula sheet, find us a formula that involves those 4 variables, which I believe was distance equals velocity final times time. Is this the minus 1/2?
Yeah.
Minus 1/2 of AT squared.
This, not that good?
This negative means we're going to try to slow down. But this 2.0 meters per second is a positive number because we are still going to be going forward when we're done. What if we wanted to be going backwards? Well, then this would then be a negative number. So if you're going forward, it's a positive number. If you're going backwards, it's a negative number. If you're speeding up, positive number. Slowing down, negative number. Does that make sense? So let's plug in some values then. Velocity final, 2.0 meters per second times by my time, 20 seconds. Right off the bat, you probably will recognize that the seconds are going to cancel, right? So you can even cancel those if you want. Minus 1/2 of A. Okay, well this is a negative 4.5 meters per second per second. I'll just write it like that. And then my time, again, for a second time, 20 seconds. How are these units here going to cancel? Well, see how this seconds here is squared, right? Essentially, there's 2 seconds symbols, right? Which means that both of these second symbols will be able to eventually cancel these ones. So I'm going to go right to my unit here. This is going to be a meters unit. And this half over here is also going to be a meters unit. That's good, right? Kind of makes sense they should both be meters units. So by the time I'm done, I'm going to have a meters unit. Okay. Last step. We're just going to throw this all in our calculator at once. I know there is some multiplying and some dividing. General consensus is that if you're just purely adding or purely subtracting, do that sig dig rule. But if you ever do some adding and some multiplying, go to the multiplying sig dig rules. So when we're done, we get to have 2 sig digs. Does that work? So now you just need to know how to operate a calculator. Make sure you catch that negative 4.5, right? What'd you get? 940? That's what I got too. Okay. Well, that kind of makes sense, doesn't it? Wasn't this a train? Trains don't slow down overly fast, right? Like it's going to take a kilometer for it to slow down quite a bit here. So. Is 940 meters though going to work with sig digs? We only get 2 sig digs, right? So make it either 9.4 times 10 to the 2 meters, or make it 0.94 kilometers, something like that. I don't care. Just find a way to change the sig dig so that there's only 2 of them left. That's a 0, by the way. Right, again. Does that work? Alright, why don't you guys try this one? I've done a few. Parachuter deploys his parachute 1.53 kilometers. Take note of units. We probably can't work with kilometers, so we'll have to convert. Above the ground. He decelerates at a rate of 6.3 meters per second per second. Takes him 25.7 seconds to hit the ground. How fast is he going? How fast was he going when he initially opened the parachute, though? See if we can get the scenario here. The guy's already free falling, right? He then opens his parachute. He opened his parachute 1.53 kilometers above the ground. It started to slow him down, so he wasn't going quite as fast as he was anymore, because he was going pretty fast, right? He's going to keep speeding up until he hits terminal velocity and then it's flat. So he decelerates at 6.3 meters per second squared. Took 25.7 seconds for that to happen. How fast would he go then? I lost him again. So if you're really stuck on where to start, I think most of you seem to have got started at least. The four variables we're looking for are distance, acceleration, time, velocity, initial. Oh. You guys back? There we go. That's frustrating. I'm getting super sketchy reception from you guys right now. You're glitching like crazy. Can you guys still hear and see me? Okay. Okay, so we're just working through this example here. You guys had a chance to try it? So we know our distance is 1530 meters. I made that conversion from kilometers in my head. We're looking for an initial velocity. We know our time, 25.7 seconds. Our acceleration, negative 6.3 meters per second squared. Very rapidly running out of room here. 25.7 seconds squared. Everybody able to get to that step there? You're able to like plug all the numbers in the formula? You guys feel comfortable doing the algebra for this in order to make this work, or should I walk you through step by step how to isolate for VI right here? Mathematically, how do I get VI by itself? What do I have to do first? That 25.7 is probably the last thing you can do. You can do it first, but I'm going to suggest that since there's a plus sign right here, find what this number is right here, that whole value there, and throw it on the other side. And then lastly, divide by the 25.7. That makes sense. In a way, it's kind of like 3 equals 2x plus 7. This is your 3 right here. This is your 2x. And then this whole shebang over here, I mean, it's gross, but it's just a number, right? So find what that number is, subtract it from both sides, and then divide. So if I do 1/2 of negative 6.3, oh, I missed the negative here, didn't I? Because we're slowing down. Negative 6.3 times by 25.7 squared. I found this number right here then to be negative 2080.54, kind of thing like that. It's a negative number though, right? So then we need to add it to the other side. So 1530 needs to be added to 2080.5435. So at some point, sorry, I'm running out of good room here. I ended up getting like a 3610.5435 equals your velocity initial times by 25.7. That's kind of where the math ends up being. And so then I would divide by your 25.7. Yeah, okay, so I've been skipping that, haven't I? So what ends up happening right here, Jimmy, is the meters per second squared right here ends up canceling. So that, you know this number I had right here, the 2080.54, that's a meters number then. Which means that when you add it to this number right here, it's a meters number. But this number here is a seconds number. So when we divide a meter by a second, we get our typical units for velocity of meters per second. Okay. Long story short, I got 140.488 or so. Here's a good talking point. You should never round a value until you are done the entire thing. So sorry that it's kind of a mess here. This 2080.54, that sort of number there, you should use that whole number out of your calculator if you can. So some of you have TI-84 calculators and you can like scroll back up to find the value. If I haven't shown you this before, this is a really useful skill. So I'm just going to pull a calculator up here on the screen so you can all see it. Let's say you did a big calculation and you calculated 0.5 times negative 6.3 times 25.78 squared. And you recognize that this is a number that you need to work with. Maybe I typed it in wrong. Anyways, say that's a number you need to work with. Okay? Your calculator, regardless, so long as you have a TI one, you can store a number. Press this button right down here, STO. See that one right there? And then what we have to do is have to assign a letter to it. And your calculator, see how there's like letters hidden behind here, like A, B, C, D, E, F, G, like that? If you go alpha math, it will bring up the letter A. This will now store that number as A. So then later, in case you need to use that number again in the future, that whole number, all of those digits included, will be there. So if I then want to take 1,000 and add that number, A, oops, did that wrong, alpha A. Essentially what it did is it added this number to 1,000 for you. So that way you can always keep an infinite number of digits until you find the finish. The worst thing you can do is do little rounding errors along the way. Don't you dare round this number to 2080 and then make this number here 3610, right? Because the more you round along the way, the worse it's going to get. So, anyways, I got 140.488, something like that. You guys get that too? And then the units would be meters per second then. We just got to hit up sig digs then. 2. Alright, so 1.4 times 10 to the 2 meters per second. One more thing though, it actually asks for a velocity. Make sure you watch that carefully. Since it's a velocity, we need to know which way he's traveling. Say it louder? Yeah, that makes most sense. D for downward. Right, because he's skydiving. That makes sense. He starts skydiving, he's free falling, he's going 140 meters per second. That's about right. That's about terminal velocity, give or take. Right? And then he opens his parachute and starts to slow him down a little bit, so he's not going quite so fast. Is he still going down though? Yeah, he's still falling. He's just not falling quite as fast as he used to be, right? Which is good, because otherwise if he hits the ground at 140 meters per second, that's not going to go well. Right? You guys see that video over the summer of the guy who skydove without the parachute? We need to look this up. Yeah, massive, massive, massive nets. Jumps out of an airplane from way up there, no parachute. Yeah, and manages to land it like on this net. I'll YouTube it for later. Absolutely incredible. Couldn't imagine doing that. Alright, anyways. Okay, that was our last one. You guys have any questions? Quick summary then. I need you guys to be fairly comfortable with algebraic formula manipulation. As you can see on your formula sheet, you're going to get a lot of formulas. We're starting to work with a few of them, because really they're just a holdover from grade 10. If I give you the information, you need to know how to throw it in the formula, rearrange it, get the answer. So, we've got a little time left today, not a lot. Tomorrow is meant to, what happened here? Tomorrow was meant to be a work day for you guys to practice this. Because truthfully, like, this was like 2 solid weeks of grade 10, at least in my group. You guys did like a week. So my recommendation would be, at some point, either download it to your phone, or if you want to print it. Are printers up and running yet? Okay, I'll keep printing stuff for you then. Find that document that I posted on my website. Tomorrow, practice some of these, right? Just get in the habit of redoing basic algebra. So it's right here, review questions. So I mean, if you want to, do sig digs, do calculations, but I mean, there's a lot of questions here. So I don't really care which ones you pick. You guys have any questions of me? Life is good. Alright, sounds good. Alright, well, find something to keep you busy for 10 minutes, I guess.